So I'd like to try and relate the differences in the standard reduction potentials in two respirations to the size of the proton motive force that they produce, and therefore how much ATP they produce. So let's start off with a respiration that you're familiar with. So the respiration that humans do in their mitochondria is carbohydrate plus oxygen to carbon dioxide and water. And then obviously if you reverse that process, that's effectively photosynthesis. So if you think back to our standard reduction potential tower, is what you probably remember, is that electrons are going to flow from the carbohydrate to the oxygen, and they'll do that spontaneously. And we speed those reactions up with enzymes, obviously, and that will yield carbon dioxide and water. And so because the standard reduction potential of carbohydrate and oxygen are well separated on the redox tower, that means that the difference in the standard reduction potentials is going to be relatively large. So what does that mean? That means that in your cells, in mitochondria, you can make a larger, or you can make more proton motive force. Remember, the proton motive force is the difference in the proton concentration across the inner mitochondrial membrane. And so the larger that proton motive force, the more ATP you can produce. Now let's compare that to a different form of aerobic respiration. So let's just change the electron donor. So let's make the electron donor nitrite. And so this isn't as negative on the standard reduction potential scale on the redox tower, but we'll give it oxygen, so that's pretty positive in terms of its standard reduction potential. So electrons are going to flow from the nitrite to the oxygen during this respiration, and that's just going to give us nitrate, so don't worry about that. That's obviously, you can see it's more oxidized, it's got more oxygen, so it's more oxidized. Now when we do this respiration, the difference in the standard reduction potentials here is smaller because there is less difference between the standard reduction potential of the electron donor, which is nitrite, and the electron acceptor, which is oxygen. And I say smaller here because I'm thinking about this relative to the difference in the standard reduction potentials between carbohydrate and oxygen that we just talked about. So if we have a smaller difference in the standard reduction potentials, that means we're going to have less of a proton motive force relative to what we did in the respiration with carbohydrates, and so that means that you're going to make less ATP. So there is a clear relationship, and I'm not saying it's a directly proportional relationship, there's a clear relationship between the differences in the standard reduction potentials of the electron donors and acceptors in different respirations, the magnitude of the proton motive force that can be generated across a membrane, and the amount of ATP that can be produced by that respiration.